Hello. Today we reach lecture 17, and in today's lecture we will start talking about a new topic, which is chapter 35. It's about a particular type of waves, which are light waves. Okay, so we will learn about light and optics and such things. So what is light? The light is an electromagnetic wave, so it's a wave that can travel through vacuum with a speed c equal 3 times 10 power 8 meter per second. The speed of light decreases when the density of the medium increases. So for example, density of air is less than density of water, less than density of a glass, implies velocity in air is larger than velocity in water, and it's larger than velocity in glass. So it's 3 times 10 power 8 in air, 2.25 times 10 power 8 in water, and 2 times 10 power 8 in glass. Behavior of light can undergo either reflection or refraction, and this is what we will learn about today. So what happens under reflection? If you hit light on a smooth surface, it will get reflected. Okay, this type of reflection, we call it specular reflection. However, if the surface is rough, we will notice that the reflection doesn't look very pretty. Okay, and this type of reflection, we call it diffuse reflection. Now, what is the rule of reflection? The incident angle will be reflected by exactly the same angle. So if this angle is 30, this angle is 30. Okay, let's do an exercise. Two mirrors making an angle of 120 with each other. So this angle over here is 120. This angle. Okay, as illustrated in the figure. A ray is incident on the mirror at an angle 65, which is this angle over here. And this is mirror 1. It is a smooth surface. Okay, so the mirror is one example of a smooth surface. Find the direction of the ray after it is reflected from mirror 2. So what we need to find is this angle over here. Theta mirror 2 and theta prime. Of course, these two angles are equal to each other, and we need to find their value. So we know, let's now draw in purple. We know if this is 65 over here, then this angle over here is also 60. Sorry, if this is 65 over here, and this angle here is 90, so this angle over here is 25. Which is 90 minus 65, right? This angle over here is 25, delta. Now, if this is 25 and this is 120, gamma is 35, because the sum of the three angles in a triangle is 180, okay? And 35 plus 25 plus 120 gives me 180. Now, if this is 35 and this here is 90, then I get theta, this theta over here is 90 minus 35, and this is 55. I'm sorry, it's not easy to draw. So this angle here is 55. If this is 55, then this is also 55, because this is the law of reflection. Okay, you can find the full answer over here. So first, I calculated this angle X, which is 90 minus 65. Then I calculated angle Y, which is 180 minus 120 minus X, and this is 35. But this angle is 90, so this angle is 55, and it's the same as theta and 2. Okay. So this is wave under reflection. Now, what is wave under refraction? I'm sure you've seen this before in school. If I put a pen, and I remember that's the example that our teacher gave in class, that if I put a pen over here, we will see as if the pen is broken. Okay, in reality, it's not broken, it's just refracted. Okay, it just gets refracted. When light passes from a medium to another, the beam of light changes its direction of propagation. We call it refraction, due to the change in the speed of light at the boundary, because the speed of light in air is different than the speed of light in water. This is why we will observe that the object will change direction. Now, what are the rules? When the light passes from a medium with high speed to another medium with lower speed, so for example, from air to water, because the speed in air is higher than the speed in water, the beam of light moves toward the normal. So we will see that theta refracted is less than theta incident. Okay, theta I is theta incident. Theta I is theta incident. And theta R is theta refracted. Okay. However, when the light passes from an area with velocity lower than the other area, then the refracted beam moves away from the normal. Okay. Now let's look at some definitions. The index of refraction, N, is the ratio of the speed of light in vacuum, which is C, which is a 3 times 10 power 8. So C is 3 times 3e to the 8 meter per second, divided by the speed of light in that medium, and N doesn't have a unit. So let's take some examples. Velocity in air is a 3 times 10 power 8. Velocity of light in water is 2.25 times 10 power 8, and velocity of a glass is 2 times 10 power 8 meter per second. So N for air is C over V of air, which is C over C is 1. N of water is C divided by 2.25 times 10 power 8, which is 1.33. And N index of refraction of a glass is 3 times 10 power 8 divided by V of a glass, which is a 3 times 10 power 8 over 2 times 10 power 8, which is 1.5. Notice that V in air is higher than V in water, is higher than the speed in glass, but we obtained that the index of refraction of air is less than that of water, is less than that of a glass. So as the velocity of light increase in a medium, the index of refraction decrease. Okay, the medium with high index is a medium which is more refractive. Okay, so we say water is more refractive than air, or air is less refractive than water. Snell's law. So we agreed that law of reflection is theta incident equals theta reflection. So what is law of refraction? Okay, so if I have an incident angle, how it is related to the refracted angle? It is related to it obeying this law. Ni sine theta I. So this is here I, and N1 sine theta I, okay, is equal to N2, because here it's called N2 sine theta R. Okay, this is theta R over here. This law is called Snell's law. Let's see how we can apply it. For example, we have that theta incident is equal 50 degrees, and the question is to find theta R, and we have that index of refraction of in air is 1, and the index of refraction of glass is 1.5. So we apply N in air sine theta I is equal N of glass sine theta R, or theta R is equal sine inverse of, actually we can apply this easily, N of air is 1 times sine theta incident, so sine angle 50 is equal to 1.5 sine theta R. Okay, now we multiply 1 by sine 50. We divide it by 1.5. So this is what's happening here. This is 1 times sine 50 divided by 1.5. And then I take sine inverse, because here I have sine of theta R. So I get theta R is equal 30.7. Notice that it is less than 50. Okay, because we're moving from a medium with lower index of refraction to a higher index of refraction. So the angle will be toward the normal. Okay, let's look at what happens to the wavelength. So when a wave passes from a medium to another, its frequency f remains constant. So in medium 1, we have frequency 1, v1, lambda 1. In medium 2, we have f2, v2, lambda 2. But we're saying that f1 is equal to f2. And we know that v is lambda f. So now we know if lambda increase, v increase, because the relation here is directly proportional. But if I take lambda 1 over lambda 2 is equal to v1 over f over v2 over f, the f and f cancels out. This is v1 over v2. And instead of v1, I will put c over n1, obeying this formula over here. Okay, divided by c over n2, the c and c cancel out, and I will get lambda 1 by delta 2 equal n2 over n1. Now, behavior of light during refraction. If we are moving from a medium to another more refractive medium, that is n1 less than n2, okay? Or v1 higher than v2. Now we know that if we go from one medium to another more refractive medium, n1 will be less than n2 and v1 will be higher than v2. Now, what are the three special cases? If theta initial equal to 0, theta r will also be equal to 0, no deviation. If the angle is between 0 and 90, the refracted angle will be toward the normal, okay? And then if theta initial is 90, the refracted angle will be called theta critical, okay? We can obtain these angles by obeying Snell's law, which is n1 sine theta 1 equal n2 sine theta 2. Now, what happens if we go from one medium to another less refractive? That is, n1 is higher than n2 and v1 less than v2. The first case is the same. If theta incident is 0, theta refractive is equal to 0. Okay. If theta incident is between 0 and theta critical, the beam of light will move away from the normal. And if I hit it with theta critical, it will be refracted at an angle 90. And if the incident angle is higher than theta critical, between theta critical and 90, total internal reflection will happen, okay? So these are very special cases. All of them you can calculate. So here and here and here, you can calculate the angle using Snell's law. Now let's summarize. If n1 is less than n2, there are three special cases. Theta initial equal 0, theta refracted is equal to 0, no deviation. If theta initial between 0 and 90, theta refracted is less than theta initial, which means that it will move toward the normal. If theta initial is 90, theta refracted is theta critical. This is the maximum angle of refraction. If we're moving from n1 higher than n2, theta initial equals 0, theta refracted equals 0, theta initial between 0 and theta critical, the refracted ray moves away from the normal until theta initial is exactly theta critical. This will give theta refracted 90. And finally, if I exceed this theta critical, if theta initial between theta critical and 90, total internal reflection occur and the surface of separation acts like a mirror. Okay, so by this, we reach the end of today's lecture. In next lecture, I will be solving exercises so as we understand all these things from today's lesson. Bye-bye for now.